You ever wonder how we find those tiny, invisible security flaws hidden deep inside the software that runs, well, everything? Your phone, your laptop, these aren't just little glitches. They can be unlocked doors for attackers. Today, we're going to look at a brand new automated detective, one that's designed to find and lock those doors before anyone else can. Let's dive in. So let's start with a question. If you were a bug hunter and you were looking for the most critical, system-crashing vulnerabilities you could find, where would you even start looking? It's probably not where you think. It's not in the apps you use every day, or even in the menus and buttons you click on. The real answer is right here, deep inside the kernel. You gotta think of the kernel as the central command for your entire computer. It manages memory, the processor, how all your hardware talks to your software. It's the foundation everything else is built on. And a bug here, it can bring the entire house down. Okay, so if the kernel is that important, you'd think it would be locked down like Fort Knox, right? Well, not exactly. It has this kind of weak points, almost like an unlocked side door, that, believe it or not, makes up a huge part of its code. And this chart right here just perfectly illustrates the problem. See, the vast majority of the kernel's code isn't the core system itself, it's the drivers. These are all the little pieces of software that let your operating system talk to your graphics card, your printer, you name it. And the research is clear. This is where most kernel bugs are found, simply because there are so many of them and they often don't get the same security scrutiny. So how do we actually find these hidden bugs? Well, the best technique we've got is called fuzzing. Imagine you're stress testing a brand new bridge. You wouldn't just send a few normal cars over it, right? No way. You'd send trucks that are way too heavy, cars that are too wide, maybe even try to drive a few sideways. Fuzzing is basically that, but for software. It just bombards a program with tons of random, malformed data to see what makes it crash. Now, fuzzing is incredibly powerful, but even the best bug hunter in the world, this veteran detective of the software world, has a pretty big blind spot. And that veteran detective has a name: Syzkaller. I mean, this thing is a legend in the security world. It's responsible for finding thousands of bugs in the Linux kernel alone. Its track record is just incredible, but it relies on one thing that's really, really hard for humans to provide. See, to do its job right, Syzkaller needs a map. The technical term is a syscall specification, but think of it as a guidebook, hand-drawn by human experts, that tells the fuzzer how to interact with a piece of code. The problem is, creating these maps is super tedious, it's slow, and it takes a ton of expertise. And because there are so many drivers out there, most of them just don't have a map. They're basically uncharted territory. Now, the biggest challenge in drawing these maps is dealing with something called an explicit dependency. This is a fundamental rule that says you can't just run commands in any random order. Often, one command has to run first to give you a special key. It's called a handler, and the next command is totally useless unless you provide that exact key. Let's make this really simple. Think of it like a library. First, you have to run an open command. That's like going to the front desk to get a library card. The system gives you back a unique number. That's your handler. Then, when you want to run the read command to actually get a book, you have to show them that specific library card. A fuzzer that's just guessing random numbers will almost never guess the right one. It's just not going to happen. It needs the map. And this is where our new tool comes into the picture. Researchers realized that if they couldn't count on people to draw all these maps, maybe, just maybe, they could teach a machine to figure it out on its own. And the key to the whole thing was finding a simple, hidden pattern. So this is the crucial shift in thinking. We're moving away from the old, slow, painful method of manually guessing and writing these maps to a brand new automated way, where a tool called SyzGen++ can actually recognize the underlying patterns in the code itself. And here it is, the aha moment. The researchers behind SyzGen++ figured out that these seemingly complex rules, these dependencies, almost always follow a very simple two-step pattern. And that simple insight is what makes all the automation possible. This is the core pattern SyzGen++ is trained to find. First, there's an insertion. One part of the driver creates a new resource and sticks it into some global list or array. Think of it as putting a new book on the library shelf. Then there's a lookup. A different part of the code takes that handler, our library card, from the user and uses it to find that exact same resource on the list. By automatically spotting these pairs of insert and lookup operations, SyzGen++ can basically draw the map all by itself. So the theory is pretty brilliant, right? But the question that really matters is, does it actually work in the real world? Let's take a look at the results. And the answer is a huge yes. For all those drivers that had no maps whatsoever, SyzGen++ went in and automatically uncovered 245 previously unknown dependencies. It was literally drawing maps for completely uncharted territory. This slide really puts it into perspective. It shows something called code coverage, which is just a measure of how much of a program's code the fuzzer actually managed to test. And as you can see, SyzGen++ just blows the other state-of-the-art tools away. We're talking an average of 71% more coverage than a leading tool called DIFUZE, and more coverage means more chances to find bugs. And find bugs it did. Using the maps it created, SyzGen++ discovered 10 brand new, previously unknown security bugs. And get this wasn't in some obscure piece of software. This was in the Linux kernel, one of the most heavily tested, scrutinized codebases on the entire planet. Now, this wasn't just some academic exercise. 6 of these bugs were serious enough that they were assigned official CVE numbers. That means real-world security patches went out that are now making millions of Linux-based devices, from massive servers to the Android phone in your pocket, that much safer. Okay, so let's step back for a second and just summarize what this all really means. This isn't just about a clever new tool. It's about a pretty fundamental shift in how we secure the very core of our digital world. The takeaway here is really clear. We started with the problem: kernel drivers are a massive and often overlooked source of risk. The old way of doing things, manually creating maps for bug hunters, it just can't keep up. SyzGen+ solves this by automatically figuring out those critical hidden rules, and that lets our bug hunting tools explore deeper and find more bugs, which ultimately makes all of our systems more secure. And that really brings us to a final, bigger question. This research shows how we can automate the discovery of hidden, complex relationships in software to find these security flaws. It kind of makes you wonder, if we can teach a machine to see these invisible rules in code, what other huge, complex, hidden problems in other fields could this kind of automated pattern recognition help us solve next?